So slanted asymptotes, folks, it's part of our study of rational functions. So let's go and review all our rules for rational functions. So if I give you something like a 1 over x plus 3. Okay, we've graphed this several times already. And we say the first step is to find the vertical asymptotes. And the vertical asymptotes is when the denominator is equal to 0, and we find it at 0 when x equals to negative 3. So if I plug in x to negative 3, we said we divide by 0, and that's a no-no for us, so x can't be negative 3. So we have a vertical asymptote, let's write it this, vertical asymptote at x equals negative 3. So on the graph, easy peasy, at negative 1, 2, 3, we put a vertical line dot down. All right. Second step, look for horizontal asymptotes. Now horizontal asymptotes, we have 3 rules. Is the top bigger, the bottom bigger, or they're the same? So let's do the easy one first. If the bottom is bigger, let's use it as x to the m on top and n on, let's do n on top and m on the bottom. Oh, come on. M on the bottom. So if m is greater than n, okay, rule number 1, we have, that means 1 over, let's say, x squared, the bottom is bigger. Our horizontal asymptote, y is equal to 0. Why is y is equal to 0? Because as x gets bigger, we end up dividing by a large number, let's say 1 over 100. And isn't that really close to 0? Isn't that a small number? That leads us to a small number. Small number close to 0 pretty much leads us to 0. What if they're exactly the same? If m is equal to n, if the exponents are exactly the same, x squared over x squared. We said, let me stick a 2 and a 3 here. We copy the front numbers. So their horizontal asymptote here is y is equal to 2 over 3. Why is it? Well, as numbers get bigger, this will be 200 over 300. That's 2 over 3. 2,000 over 3,000. And as x gets bigger, it doesn't change the fact that this becomes 2 over 3. For our horizontal asymptote for this problem here, we are, rule number 3 though, that was 2, and now that's 3, is if n is greater than m. Is n is now bigger than m, the top is bigger. And we said if the top is bigger, let's say x squared over x, the top is bigger, we have no horizontal asymptote. And we're going to come back to this last rule here, and that's the rule that we're going to study today. So what happens in all these situations, all these possibilities, can we make a guess of what the graph will look like? Now let's finish the graph that we started off with. We said a vertical asymptote was 3, or her horizontal asymptote followed number 1 because the bottom was bigger. We have 1 over x plus 3. That's bigger than the bottom. Okay, perfect. That means our horizontal asymptote is at 0. So we said we're going to go ahead and draw a dotted line at 0. And then we're going to pick some values to graph. We could try looking for zeros on top. There are no zeros on top. The top is just a 1 value. So let's pick up some numbers. Let's pick on the right side. Let's plug in 0. 0 is always easy. 1 over 0 plus 3 is 1/3. That's a positive number, so we're going to be up here. So we know we're going to be stuck on top. On the left side, I'm going to pick negative 1, 2, negative 3, negative 4. Let's plug in negative 4. 1 over negative 4 plus 3 equals to 1 over negative 1. Hey, that's just negative 1. Great, negative 1 is about here. We're going to be stuck on the bottom. All right, absolutely beautiful, right? Easy peasy. I'm hoping easy peasy. All right. So this was our basic idea of how to graph rational functions. We look for vertical asymptotes, we look for horizontal asymptotes. That gives us an idea of what type of shape this would be. Then we start plugging in values to figure out where should we really graph. Now our rule number 3 is where we're going to leave off when it comes to horizontal asymptotes here. And the rule was when the top exponent is bigger than the bottom. If the top exponent is bigger than the bottom, we end up with this dilemma. X squared over, let's say, x plus 1. And this falls into rule number 3. The top is bigger than the bottom. So we said there's no horizontal asymptote. But here is an exception. Well, not an exception. This is an addition. Here is our add-on. This is our bonus content. This is our DLC, guys. DLC. Is that if the top is bigger by 1, okay, exactly bigger by 1 exponent. The top is bigger by exactly 1 exponent. I promise you we have a slanted asymptote. Nope, that's asymptote this way. A-S-Y-M-P-O-T-O-T-E, asymptote. And that's our general rule. Now, why is it that we have a slanted asymptote, and what does that mean? It means this. Let's go ahead and take a look at a graph. We first started graphing vertical asymptotes, right? These were not hard. So vertical asymptotes go something like that. Sure, easy peasy. We know for sure those won't work. And we said horizontal asymptotes happen if it follows two of our 3 rules. If it's the bottom's bigger, we're at 0. If they're the same, we divide them, whatever that value would be. And if the top is bigger, we said there's no horizontal. But the rule also claims that if it's bigger by exactly by 1, we have something called slanted asymptote. And a slanted asymptote looks something like that. That's a slanted asymptote. Now, why is a slanted asymptote a thing? It's like a bridge to nowhere. Here's what we're going to look at. The graph will look something like this. Okay. Now, why does it look like this? Now, let me give you the idea here. If we were just dividing, if we just had the problem, let's say x here. Okay, if we had just the problem x, isn't a graph of x something like that? The graph has no problems here. It's just nicely flowing along, doing its thing. Okay, that's the graph of x. Now, what if I say, hey, I want to mess up this graph. And we divide this by x minus 1. And I'm going to make this a squared here. X minus 1 squared. Okay? Now, looking here, oh, let's do x plus 1. What value are we not allowed to use anymore? We're not allowed to use -1. So at -1, we end up throwing an earthquake, breaking up this graph. Okay? So you could say this graph ruptures. It's almost like it's going to break, right? It's going to break. But this graph is going to break in an interesting way because at -1, when x goes to -1, y shoots off to infinity. So instead of this graph coming in nicely like that, it takes off and breaks off and shoots off to infinity up here. Okay, remember we said we were first on this road here? Instead of going to negative, oops, I messed up here. Graph there wrong, -1. Oh yeah, that's right. This is -1, right? And then I messed up here, darn it. I redrew it, I messed it up. Okay. And then my original graph we said was this guy here. Darn it. We said we broke it off. And on the other side, the graph should have connected, right? It should be going on this path. But it broke off and it's going to go to negative infinity. And what happens to this graph? This graph follows this slanted line forever. It follows this slanted line forever. Now let's go ahead and graph this graph here. X squared divided by x plus 1. And let's take a look at Desmos and see what that tells us what this graph looks like. X squared divided by x plus 1. Now if you take a look at this graph, it looks very similar to what we drew. We said we're not going to exist at x is equal to -1. So we said we have a problem there. And now here's also the next part we mentioned, that we have a slanted asymptote. Now how do you come up with what is the equation of the slanted asymptote? We use long division. X plus 1 divided by x squared. So we use long division to figure out what is the equation of our slanted asymptote. All right, let's use long division. X goes into x squared, one time, x. X times x is x squared plus x. Subtract, negative, negative. We have negative x. Bring down negative x. How can I make x become negative x? That's negative 1. And then we multiply negative 1 times x is negative x minus 1. Okay, we're going to go ahead and finish it off. Oh, sorry, that's a 0 there. I'm sorry. We're going to multiply it. Thinking of too much stuff in my head. Negative x minus 1. We subtract it, and we're left with a remainder of plus, that's a 1. So remainder, 1 over x plus 1. Now this is the most important part of the takeaway here. When I use long division, if you please notice that how many times does x plus 1 go into x squared? The answer is x minus 1. Great, fine. Now this is our slanted asymptote. Slanted asymptote. Y is equal to x minus 1. What happens to this guy here? What happens to the 1 over x minus 1? Well, let me ask you on the graph to the right. As x gets bigger, as x gets bigger, what happens to that fraction? 1 over x plus 1. As x goes to infinity, what happens to y is equal to 1 over x plus 1? As x gets bigger, if I plug in 10, 100, 1000, what's 1 over 1001? Isn't that approximately 0? And this is where slanted asymptotes come into us, like where it's important for us, is that slanted asymptotes tell us where does the graph eventually end up. And the graph ends up on the slanted asymptote. Y is equal to x minus 1. Please take a look at the graph, the solid black line here that you see on my left. The graph eventually looks like, if I zoom out a lot, isn't the graph really just x minus 1? Where do we have a problem? We have a vertical asymptote at x is negative 1. And that's where we break off to infinity. So at negative 1, here's negative 1, our graph shoots off to infinity. As x gets larger, we don't flatline. We don't flatline to 0. We don't flatline to 0. We don't flatline anything. We become the line. Now, why is that again? Let me ask you. Oh gosh, freaked me out. Hi, Didi. Oh my goodness, that scared me. My son freaked me out. Oh gosh, did you guys see that coming? My goodness. So let me ask you this follow-up question. If I say 200 divided by 100, isn't that pretty much 2? What's 200? What's 2000 divided by 1000? That's 2, right? This idea is that when we divide things, a small change, as things get bigger, when it comes to our fractions, they become more the same, approximately 2. That's what happens here. When we were dividing this ugly equation up here, x squared by x plus 1, what do we end up with? We end up with a whole number of x minus 1. That's what the graph will look like eventually. Because as x gets larger, this becomes smaller. So if I give you $101, no, actually, let's do this another way. If I give you $1, $1 is a big deal. But how about you $10 plus 1, $11? Is that $1 still a big deal? Kinda. But as I get larger, $101, that $1 doesn't make as much of a difference anymore. How about $1 and $1,000? Does it matter as much? Not really. How about $10,000 and $1? Right? Remember this idea, that's the remainder. That's the $1. Does it matter as much? No. Okay, so eventually we start forgetting about that $1 and just look at that front number. And that's this idea of a slanted asymptote. This graph in the middle, it is mass chaos. By the vertical asymptote, we shove off to infinity, mass chaos. But eventually, look, that's just the graph of a line, and we become closer and closer to that graph of a line. Let's do another example here. Okay, so my question here is, oh shoot, what happened to it? Okay, let me give you this question here. 12x squared minus 16x minus 1 over 2x minus 3. Okay. I'm going to ask you guys one question first. Step 1, find the vertical asymptotes. What is my vertical asymptotes for this graph? That's when the denominator goes to 0. In this case, it'll nicely go to 2x minus 3 is equal to 0. 2x equals to 3. X equals to 3 over 2. Okie dokie. So I can graph my graph at positive 1, 2, at 3.5 right here. Vertical asymptote. Got it. Okay? That's my belief. Let's look for horizontal asymptotes. Are there any horizontal asymptotes for this graph? The top is bigger, the bottom is bigger, or they're the same? The top is bigger, so we have no horizontal. Guaranteed, no horizontal asymptote. But we have a special rule. Oh, that was a terrible start. But special rule is that if the top is bigger by 1, we do have a slanted. So we need to find out what that slanted asymptote is. So we do long division. 2x minus 3 divided by... Hey, can you close the door? Thank you. 12x squared minus 16x minus 1. I heard him come in that time. So let's go ahead and divide it. 2x goes into 12x 6x times. Okay. We multiply down. We end up with 12x squared minus 18x. Minus plus. We end up over here at 2x minus 1. Keep going. How many times does 2x go to 2x? Exactly once, plus 1. And we multiply 2x minus 3. Negative, negative, positive. That becomes a plus 2. We have a remainder of 2 over 2x minus 3. Now my follow-up question is this. Given our new problem here, 2x squared, so 12x squared minus 16x minus 1 over 2x minus 3 is exactly the same graph as 6x plus 1 plus 2 over 2x minus 3. They're exactly the same graph. They're exactly the same value. We just divided. What's the difference between 6 over 3 and 2? Nothing. I just divided it. They're the same equivalent value. What's the difference between 7 over 5 and 1 and 2/5? Nothing. They're exactly the same thing. So I want to tell you guys that this graph here is the same graph as this one here. But there's a hint to this new graph. Is that the graph would eventually look like this guy. When x is big enough, what's 2 divided by 200? What's 2 divided by 2,000? What's 2 divided by 2 by 20,000? Doesn't this get closer to 0? So as x gets big enough, this actually goes away and we're left with this slanted graph, because that's what the graph is going to become. And that's the goal of this lesson, to show, hey, that's what the graph will become. Not the horizontal asymptote, but this slanted. And that's going to graph it. Put one up, and the slope is 1, 2, 3, 4, 5, 6 over 1. There's going to be some crazy line going up like this. Okay. So how do I know how to complete the graph? Well, the graph could be going up here, one of these directions. It could be going down here, right? We don't know which of these 4 possible endgames we'll end up with. So what we do is we end up just plugging in values. Just like what we did before. So let's plug in 0. Isn't 0 easy? 0, 0, 0. We end up with negative 1 over 3. That's positive 1/3. And positive 1/3 looks right here. It looks like I'm going to be stuck on the bottom here. You could also have used quadratic formula on this one or factored it to see if this was factorable. I don't think that's factorable in my brain. Okay. We could factor it or use quadratic formula. That would total us our zeros. And on the right side, if I plug in, let's plug in 2 here into the problem. 2 squared. Let me write it over here. Plug in 2. 12 times 2 squared minus 16 times 2 minus 1 over 2 times 2 minus 3. We're trying to figure out what this value would be. 4 times 12 is 48. Minus 32 minus 1 over 4 minus 3 is 1. Right? 4 minus 3 is 1. And we're left with 48 minus 33 is 15. 15. So my y value is 15. 15 looks like it's way up here. So we're going to be in this corner here. Now let's see if this graph turned out the way we expected. Oh, whoops, that's not good. We're going to graph these 2 times. Let's go to graph the original. 12x squared. I think I said minus 16. Yep, minus 16x minus 1. Parentheses divided by 2x minus 3. So I'm graphing this, and you can take a look here. This is what the graph looks like. It shoots off. Okay, it's not a horizontal. Let me double check. Is this the same graph as 6x plus 1? Right, 6x plus 1? This is our slanted asymptote here, folks. If you take a look, that's my slanted asymptote. Just the front part of the graph. Okay. And I'm going to include one more. I'm going to include the vertical asymptote. We said it was going to be at positive 3 divided by 2. Uh-oh. Alright. Let me change this part also. Okay, now if you take a look here, we are bounded by, oh darn it, I lost that one. We are bounded by our 2 asymptotes, our vertical and our horizontal. This graph looks way skinnier than mine. Let me go ahead and change something here to help out. Let's change this to negative 10 to 10. Alright, see, that looks a lot better, right? When we said x was 4, right? Right here, this is going to be 2, we said, right? If we're at x is 2, come on, buddy. X is 2, y we said was 15. That looks pretty close, right? 215. That's not bad. 215. When x was 0, we said was 1/3. That's not bad. We actually have zeros in the graph too. Those are our x-intercepts, and we would have found them using quadratic formula if we had to. Okay. So the idea of what we're doing here is we're learning all aspects of graphing rational functions. We learned the easy ones: vertical asymptotes, horizontal asymptote. And this is the special rule. What if the top is bigger by exactly 1? We're not bounded by a horizontal asymptote anymore. We are bounded by a slanted asymptote. Let's do this one more time. Okay, let's do this one. Okay, our problem is, I'll make this even larger. Y is equal to 48x squared plus 26x minus 28 over negative 6x minus 7. Okay, easy first version is find the vertical asymptote. Vertical asymptote is when the denominator is equal to 0. Negative 6x minus 7 is equal to 0. Negative 6x is equal to 7. X is equal to 7 over negative 6. Then x, we know our vertical asymptote. X equals to 7 over negative 6, right? Okay, easy peasy. So let's go ahead and graph that. That's a little bit over negative 1. Here's my negative 1. So right next to it, negative 7 over 6. All right, so we know there's a disruption in the force here. The graph breaks up at negative 7 over 6. So how does it break up? Well, let's look at our horizontal asymptote. The reason why I could predict that it was going to be slanted is because the top exponent is bigger by 1. Take a look. Isn't the top bigger by 1? So we have no horizontal asymptote. Horizontal asymptote is none. Or DNE, does not exist. But we do have a slanted. So let's go ahead and find the slanted. And slanted is just going to be us dividing 6x minus 7 by 48x squared plus 26x minus 28. So negative 6x goes into 48 8 times, negative 8 times. Negative 8x, we multiply down. This becomes 48x squared plus 56x. Okay. And then we subtract that. Negative, negative. We have more negatives here, so it's going to be negative 30x minus 28. We can match it. Negative 6 and 30 is a positive 5. Negative 30x, let's do minus 35 plus plus. And we can combine those values together. That's going to give us 35 plus is 7. Okay, plus 7 over negative 6x minus 7. All right. How are we doing here? Hopefully that makes sense. Now what's a slanted asymptote? The idea here is that the graph, this crazy graph, 48x squared plus 26x minus 28 over negative 6x minus 7 just looks like negative 8x plus 5. Of course, plus 7 over negative 6x minus 7. And this is our change. Right, that's our low change. So as x goes to infinity, our graph looks like that. How do we graph that? Let's go back to the top graph in which we graphed already. We're just going to graph this portion of it, the line portion. This is the chump change. You guys ever know anyone who doesn't keep change in the pocket? Like, I don't want it. You can have it. Keep the change, boss. Keep the change. And the idea here is this is just change. As x gets larger, that y value doesn't care as much about this 7 over negative 7x minus 7. Okay, it's chump change. So let's go ahead and graph this slanted asymptote. 1, 2, 3, 4, 5. Put a dot. Negative 8 over 1, negative 5, 6, 7, 8 over 1. It's going to be like that. And our slanted asymptote looks like this. These examples give me really crazy graphs. Now, looking at the graph that I drew already, hopefully you guys can see there are still 4 quadrants here. I want to erase this part so you guys can see it. Okay, hopefully you guys can see the graph. I have 4 quadrants. I could be up here. I could be over here. I could be in this corner. Or I could be on the left here. See, those are the 4 possibilities, and I don't know which one I'm at till I start plugging in values. Okay, I don't know which I'm at till I start plugging in values. So let's go ahead and just start plugging values. And that's fine. Okay, so let's go ahead and plug in some values here. I'm going to plug in a little bit to the left, a little bit to the right. One on the right is super easy. That's a 0, right? So let's plug in 0 to the problem. Here's my table. Oh my goodness. I'm going to just plug in values on the left and right. Here's my x and my y. If I plug in on the right side of negative no, was it negative 7 over 6? Or negative what? Oh, sorry, not 7 over, yeah, negative 7 over 6. We're going to plug in negative 1. On the left, we're going to plug in negative 2. Just on the right side, left side. If you want to replace the one on the right with 0, even easier, right? Even easier, because 0's on that side. So let's plug in 0. If I plug in 0, 0, 0, 0, we're left with negative 28 over negative 7, which becomes positive 4. Okay, at 0. 1, 2, 3, 4. Isn't 4 under the 5? We are stuck in this corner here. We're stuck in that lower corner. Yep. Okay. All right. Darn it. How about on my left side? Negative 2. Let's plug in negative 2 to this problem. This might be a bit of work. But know what? Let's plug into here instead. Both ways work. If I plug in negative 2, negative 8 times negative 2 plus 5 plus 7 over, careful, negative 2, 6 times negative 2 minus 7. What's that going to be? So we're ending up with 16 plus 5 plus, this is going to give us, that's a negative 2, negative 12, oh, positive 12 minus 7. So we're at 7 over 5. Hey, 7 over 5 is like 1 point something, isn't it? So let's call that 1.4. 1.4. Yeah, 1.4. So we add this up, 21, 22.4. And that looks like a pretty big number. So I'm feeling like we are stuck above this line. We're going to be stuck up here. Let's go and verify this graph one more time with Desmos. You can hear my children in the back. Yes, I can hear them too. They're super excited. We said 48. I need to clear this. Give me a new one. 48x squared plus 26x minus 28. Parentheses, divide that by negative 6x minus 7. Right, so that's the graph that we have. I want to verify this using my asymptotes. We said we had an asymptote at negative 7 over 6. Nope, that didn't come out. Negative 7 over 6. All right, that's my asymptote there. And we have one slanted asymptote one more time. Slanted asymptote at negative 8x plus 5. Now, my graph and their graph look, you know what? Not bad. All right, not bad. I didn't do that much work on this. And this is the skill about graphing rational functions. They might ask you what a slanted asymptote would be. Okay, what the slanted asymptote would be. And we can find that out by doing simply long division. Because when you do long division, that reduces the fraction to this main component. And the main component, it looks like a line. This only works when the exponent is bigger by 1 on top. Why? Why does this only work when the exponent is bigger by 1 on top? It's actually very simple. If I say x squared plus 3x, take a look, divided by x. Isn't the top exponent bigger by 1? Hey, x plus 3, it looks like a line. Even if I put a plus 1 on the bottom, it still looks like a line, but with a remainder at the end. And that's really what we're looking for. We're looking for what is that main function that this graph will eventually look like, and this is just a remainder. All right, so your homework today is going to be like 4 questions on asking for slanted asymptote, and a lot of it is just review of your horizontal and vertical asymptotes. You may be asked on the test and for other like standardized tests, like what's a slanted asymptote or which of these graphs match, and by you doing a simple long division, you can tell if that line is going up or going down, or where would you start with that slanted asymptote, which is the graph of a basic algebra one line. Cool. All right, that's it. Thank you very much.